Hi guys, I am Joseph. Today in this video you are going to learn about unit cell and its types. First, about unit cell you should learn about four terms: lattice point, crystal parameters and Bravais lattice. In lattice point is a place where atoms are present in a unit cell. And in crystal lattice is a regular repeating arrangement of a unit cell is known as crystal lattice. And crystal parameters A, B, C. These are the edge length A, and those are based on the axis. And gamma, beta, alpha. Those are the angles of a unit cell. Bravais lattice. Arrangement of this beta, gamma, alpha, and A, B, C. There are 14 possible 3D lattice. Now moving on to the types. The types can be differed into primitive, non-primitive. And primitive unit cells are the cells which have the atoms at the corners only, like this. This is the structure of simple cubic cell. Moving on to non-primitive unit cells, these are classified into FCC, BCC and ECC. FCC, face-centered cubic cell, BCC is body-centered cubic cell, and ECC is end-centered cubic cell. Now, FCC. In FCC, the atoms are present in corners as well as in each faces of a cube, like unit cell. And in BCC, atoms are present in corners as well as inside the center of the unit cell, not on the faces. And in end-centered cubic cell, the atoms are present in corners as well as the ends, two ends of the unit cell. And that's all. Hereafter, my friend will continue the next topic.
Hi guys, this is Venkat. Today I am going to explain to you how to get the relation between A and R, which is edge length and the radius of an atom in a unit cubic cell, whether it may be simple cubic cell or FFC or BCC. So, as you can see in the diagram, the atoms in the unit cell are very far apart. But in actuality, the atoms in a cubic cell are very close to them since it's a solid. They look somewhat like this. But we take it like this so that we can have a clear understanding or how to get a better understanding of the solids or the unit cells. And since we all also know that unit cells are just a figment of our imagination, which in reality do not exist like these structures. The atoms are just available in the 3D spatial lattice. So let us move on to the topic. See, for getting the relation between A and R, consider this edge where we have two atoms and the edge length is A. So when we are taking two atoms, they will in actuality look like this, where the radius of the atom is R. Since the distance between these two is A, this becomes A is equal to R. So here this is the relation between the edge length and the radius in a simple unit cell. Whereas in the FCC and BCC it changes, since in a simple unit cell there are no other atoms except in edges. But whereas coming to the FCC, here there are atoms also not only on the edges but also in between the faces, in the middle of the faces. So while calculating for an FFC the relation between A and R, we need to take use the Pythagoras theorem. See, because this is the A and this is also A, we have to calculate the distance between here. Since in an FCC we can't casually take the difference. We can't, like, since in an FCC we can't just generally take the relation between A and R like a simple cell, because we are also having a atom in the face of the cell. So we are doing this. Consider this portion of the cubic cell where this is an atom, this is an atom, this is an atom, and don't mistake these with other atoms. Here this is the face. This is the face of the cell, and here is the atom which is the face of the cell. So this is our triangle. See, as you can see in the FCC, we have the atom in the middle of the face as well. So we are considering it like this. For example, take it like this. See, since we have an atom which is going into the middle of this, the value of relation between A and R changes. So let us see how it changes. For as we are taking this triangle, like this triangle, so it becomes R plus R, which is like R, the distance between atoms, R plus R, 2R, and here also another R plus R, 2R. But here, or whereas in this case, we'll be getting as three atoms, we have to calculate the mean distance between them. So it becomes, as in from the Pythagoras theorem, 2R square plus 2R square is equal to 2 root 2. So this becomes 2 root 2. This is the mean distance. So the relation between A and R becomes A is equal to 2 root 2 R. This is in case of an FCC. And look at the BCC. In a BCC, in an FCC, we have an atom in the middle of the phase, but whereas in a BCC, we have the atom in the middle of the entire cubic cell. So while calculating the mean relation between A and R, we have to be cautious, since we have to take this triangle as to calculate this. We also have to take this triangle because we need to calculate this distance first. So let us do this first. See the dotted triangle. This is the first triangle we are calculating, so that we can get the value of this part. So it becomes, it's similar to FCC, because so it becomes 2R whole square plus 2R whole square under root is equal to 2 root 2R. So it becomes 2 root 2R. So now we are calculating for this. So here it becomes, in this triangle it becomes 2 root 2R whole square plus 2R whole square under, which becomes 4R, 2R square, 8R square plus 4R square, 12R square under root 12R square, which is 2 root 3. That's it. 4 into 3 is 2 root 3R. Therefore, A is 2 root 3R in case of an BCC. So this is how we get the relation between A and R for different unit cells. So now my friend will continue on to the next topic. Thank you. Hi guys. Now I will be explaining to you how to calculate the number of atoms in a unit cell. I mean, when I say number of atoms, I don't mean the number of atoms that we can count. That is the number of atoms that actually contribute to the unit cell. For example, you take this simple unit cell. In this we have 8 atoms if you count it physically. But if you take the number of atoms which contribute, you can see that each unit cell is a part of a group. As it is a solid, each atom in a unit cell is linked to many other atoms in the 3D spatial arrangement. So each atom in the corner is linked to 7 other atoms excluding this. So that becomes one atom is contributing to 8 unit cells. So it will be contributing only 1/8 part of the unit cell. Similarly, while you are considering in a phase, the atom in the middle of a phase of a unit cell, each phase is attached to one other phase of the other unit cell. So it will be contributing only half, since each phase is like this. And if we consider the atom in the middle of the unit cell, it will be considering to only the unit cell, since it's the middle of the unit cell, it can't get attached to any other unit cell. So it will be contributing fully, that is 1. So now let us see if, how many atoms are actually contributing in each type of unit cell. Take an FCC. As you can see, in an FCC there are 8 atoms, but all are at the corners. So it becomes 8 by the number of atoms is 8 by, as they are contributing 8 each, it will become 8 by 8 1. So in a simple unit cell there is only one atom to count, which contributes, as we can count it as there is only one atom in the entire simple unit cell. In an FCC, take in an FCC, there are 8 atoms which are contributing, there are 8 atoms in the corners which contribute 1/8 of each. So it becomes 8 plus 8 is equal, 8 by 8 is equal to 1. And there are 6 faces to a cube. There are 6 atoms which contribute to the faces. So So it becomes 6 by 2 is equal to 3, which becomes 1 plus 3 is equal to 4. So there are 4 atoms in a abscissa. Now take the BCC. In a BCC, we have 8, similarly we have 8 by 8 is equal to 1 plus, and we have an atom in the middle of the cube which is contributing only solely to itself. So it becomes 1 by 1 is equal to 1. So it becomes 1 plus 1 is equal to 2. So in a BCC, there are 2 atoms which contribute to this. So we can then, therefore we can generalize the formula as Z, where Z is the actual number of atoms in an atom, in a unit cell. So the formula can be written as Nc by 8 plus Nr by 2 plus Ni by 1. Here Nc is the number of atoms in the corner, Nr is the number of atoms in the faces, like in FCC, and Ni is the number of atoms in the middle of the center of the cubic cell. So by using this formula you can generate number of atoms in a unit cell for the cubic unit cells. Thank you.
Hi, my name is Shreyan Mandal and today I will be explaining how to calculate the density of a unit atom cell. So as we all know, the general formula for density is given by density is equal to mass per unit volume. This is the general formula. In the same way, we will be trying to evaluate the formula for a unit cell. So in place of mass, we will be writing N into MA by capital M, and in place of volume, we will be writing 1 by V. Now, by N we mean the number of atoms present in a unit cell. By M we mean the molecular mass, and by N we mean the Avogadro's number, which is given by 6.023 into 10 to the power 23. So after this, once we start with the formula, it comes something like N into MA by capital N into A cube. As we know, volume is given by A cube, since the edge of one unit cell is given by A. Now furthermore, when we are progressing, we have to calculate the formula for all the 3 parts of atoms, namely unit cell, BCC and FCC. So for unit cell, we know N is equal to 1. So for that, the formula comes to 1 into MA by N into A cube. For FCC, we know the formula, the value for N is equal to 4. So the formula comes like 4MA by N into A cube. And again for BCC, we know the value for N is equal to 2. So the formula comes something like 2 into MA by NA cube. These 3 respective formulas, if used in the problems, can give specific answers to the questions. Now my colleague will tell about another topic. Thank you.
Thank you guys, and hope you liked our video.